Hello, calculus fans. Let's talk about an error bound on Simpson's rule. So let's suppose that the fourth derivative of our function is bounded by k on the interval from a to b. And let's say that e sub s is the error involved in using Simpson's rule. Then e sub s is less than or equal to k times b minus a to the fifth power all over 180 n to the fourth power. Then let's do a problem for illustrative purposes, since after all, this integral can be evaluated exactly using the fundamental theorem of calculus. Let's compute how large n has to be to ensure that s sub n estimates the integral from 4 to 9 of 1 over x squared dx accurate to within 10 to the minus 6. All right, let's let f of x be equal to 1 over square root of x. It's not particularly hard to compute that f quadruple prime of x is equal to 105 over 16 x to the minus 9 halves. And what we want is an upper bound on this expression from 4 to 9. Now, as it turns out, this expression is decreasing on the interval from 4 to 9. So if we just plug in the left endpoint, then we'll get an upper bound. So that's 105 over 16 times 4 to the 9 halves. Now, fortunately, 4 to the 9 halves can be computed exactly, very easily. And so what we end up with is the expression 105 over 8192. Okay, so we have a nice upper bound on the absolute value of the fourth derivative of f. And again, this is all because f quadruple prime of x is a decreasing function, at least on the interval from 4 to 9. All right, now let's place a bound on the error in using Simpson's rule. So it's going to be smaller than 105 over 8192 times 9 minus 4 to the fifth power all over 180 n to the fourth. And our goal is to make this expression smaller than 10 to the minus 6. Okay, let's go ahead and solve for n. All right, so if we simplify that expression and set it less than 10 to the minus 6, we're going to get this, and our goal now is to solve for n. And as usual, we'll just isolate the n, and at this point we can compute a fourth root, and this is okay for us to use a computer or a calculator for. Okay, so we get n is bigger than or equal to the fourth root of 21,875 times 10 to the 6 all over 98,304. Okay, we put all that in the calculator to get an expression. And if we do, we'll get n is bigger than 21.7192. Now, n has to be an even number when using Simpson's rule, so we'll choose any even value of n that's bigger than 22. If, for example, this number that we had gotten here had worked out to something like 20.71, then we'd still have to go up to 22 because we can't stop at 21. When we're using Simpson's rule, we have to have an even number of subintervals. Now that we have a value of n, let's prove that this value of n gives us e sub s is less than or equal to 10 to the minus 6. All right, so we got e sub s is less than or equal to 105 over 8192 times 9 minus 4 to the fifth power all over 180 n to the fourth. We're choosing a value of n that's at least 22. So now the inequality looks like this. And if you use a calculator to simplify all this, you'll get this gigantic looking fraction. But here, now it's fairly straightforward to see that this is smaller than 10 to the minus 6. So now we've proven that if we estimate the integral using Simpson's rule with n bigger than or equal to 22, we're guaranteed that the estimate will approximate the true value of the integral to within 10 to the minus 6. Okay, that's all for now.